Welcome all. Today we will see something about intermediate code generation. As we have already seen in the last lecture something about the semantic analysis, and we have seen that how in the tree itself for each node when production reduces we write the codes so that some intermediate code can be generated from there, right? But still here we are explicitly seeing something about how these intermediate codes can be represented. We all understand one thing, that in our this compiler system, I should say analysis synthesis model of a compiler, we have a front end and a back end, right? So what happened in front end, if I'm not wrong, you will understand front end. You will have your parser, those syntactic checker, and the intermediate code generator. So then you will get something, we should call it intermediate code, right? Which can be used by code generator to generate the final code, right? Now the thing is, this is front end, this is back end. Okay, so now one thing that we can understand is front end is responsible for generating this intermediate code. Now the thing is, front end is independent of machine, however this back end is dependent on machine. What we can do, if we will not have this kind of model, analysis synthesis model, in that case what will happen, we will have just one full procedure which will generate the target code, right? It will take the source code and generate the target code, but a target code to run on a particular machine, it is dependent on that particular machine. So if we will write this program, this compiler for each machine, it will be difficult. It will what I can say, we will have to write many numbers of compilers, right? However, if we are dividing it between front end and back end, in that case we will write some set of front end and only some set of back end dependent on the machines, right? So then we can have f into b, right? If f is the number of front ends written and b is the number of back ends written, so we will get total of f into b compilers, you know? So that is why we are having this front end as well as back end. Now as we are talking about the front end, its role is to have intermediate code. Now this intermediate code should be represented in a way so that this code generator could easily transform it into the machine respective code. Okay, so this will be dependent on machine, but still the front end had to generate intermediate code. It has to be represented in a particular way, right? So here we have several representations for intermediate code. Let me say representations of intermediate code. Basically these intermediate codes can be represented either in a tree form, or we can call it linear form. Okay, so in tree form they can be you can have a syntax tree, or you can have didactic acyclic graph of this syntax tree, the variant of the tree only. Linear form can be postfix notation, or it can be 3 address code. Okay, so let me give you an example. Let us suppose the input is something like a plus b, more than this, a plus b into, suppose, a plus b plus c. Okay, so what will happen in the syntax tree? A syntax tree will be something like, select syntax tree, okay. So syntax tree will be something like, you will have this on the top, so a multiplication, then plus a and b, right? In this side you will have something associativity. This will be first now, so it will go down. This will be here. Here you will have a as well as b, and here you will have c. No problem. Syntax tree. So now you can say this is how the syntax tree is there. Now you can see one thing, that this is a plus b, which is being repeated here as well, a plus b, right? So now for DAG, what you will do, you will just reuse the existing nodes. You know that for these things you will create nodes, right? Like linked list. So you will have this thing like a node. You will store multiplication, and then you will store address of which will point this thing and which will point this thing, right? Let me take this thing. It will point this node and it will point this node, right? So now here what you are going to do, you will have to reuse this existing node, right? So plus here, so this is multiplication, right? And plus here, I should make it a little, okay, okay. So this will have a plus b, right? So here on the left hand side, if you remember, it has a plus b, and on the right hand side it has c, right? So let us have c on the right hand side, and on the left hand side let us reuse this. Okay, it is also directed acyclic. Okay, so this is how it is represented. So it is just for saying that we are reusing the existing thing in the syntax tree. Okay, if we write the same thing in postfix, how will we write? Okay, so it will be this part, then this part, and then in last it will be, right? So for this part it will be a b plus, here this will be the first, and then this, and then it will come. Okay, so a b plus c plus star. Okay, this is your postfix notation, right? 3 address code. For the same thing, if you want to write 3 address code, what happens in 3 address code? Actually you want to have such statements in which only three addresses are used. Okay, I should say you can use variables, so 3 variables are used only. Okay, operations can be used, no problem. So in 3 address code, what I am saying, you can write it as okay, for this one you will have something again. For this thing you will have, okay, let us see, let us take a temporary variable 1. It will be equal to a plus b. Temporary variable 2. Now again, for these 2 operations you can keep a plus b and then c, and then in the next one you can merge it with the c, right? So it is true that here you can reuse t1, but still let me write t2 is also a plus b. Since these things are automatically generated, so we have to take care of these things as well, right? So t2, now t3, for t3 will be t2 plus c. So from one side we are getting t1, another side we are getting t3. So now we will add these two in t4, no, multiply, right? So t1 multiplied by t3. This is how you will write this thing in 3 address code. Okay, so 3 address code is very simple, and you can write these things. 3 address code is also popular because we want to represent these things with assembly language, right? So usually in assembly language you see there are 3 address code. So we want these things actually 3 address code to be popular, right? Let me say some more things about 3 address code. Actually, suppose, what are the types of 3 address code acceptable, right? Suppose, let me write it like this: types of 3 address code. Basically I am saying what are accepted as a 3 address code. As we have seen, x is equal to something y, any operation, op, y, op, z. So there are 3 variables only, right? So it is 3 address code. Okay, we write it like this only. So another can be, if less than 3 it is okay, no problem. Suppose x is equal to opy or x is equal to y. So these all are okay. Another thing is if you are using something like array kind of things, x is equal to y and some iterator I. This is also allowed in 3 address code. You can have suppose xi is equal to y. This is also okay. If you can use the address of operator, so %y or pointer, suppose x is equal to star p. These all the things can be used. If you are using go to, suppose go to L, some level L, so it will be allowed. If you are one thing, if a statement, if x opy go to L, this is allowed. Why? Because x is 1 memory, 2 memory and 3 address, so this will work. These all are allowed in 3 address mode. So anything you are having where more than 3 variables are being used, it will not be allowed. Like suppose x is equal to y op z op k, है ना? So 3 variables plus 1 4, it is not allowed. Okay, so these are something that we were saying is something about 3 address code. There can be some assignment for you to write a 3 address code for some part of code. Okay, let me give you this example. For your assignment is to write 3 address code, right? 3 address code for let me give you for following. It will be if a is less than b, then suppose some variable t is equal to 1, else you put t is equal to 0. Very simple. So for this you can write a 3 address code. This will be your assignment. Okay, now these 3 address code, okay, you have seen that they are temporary variables and they can be written like this. Temporary variable 1 is this thing, temporary variable 2 is this thing. But for this only, what you will have some memory. Here it is I, and ith location, what you will do, you will write certain code, 3 address code. I plus 1, you will write a certain 3 address code, and so on, right? It's okay, but how these 3 address codes can be better represented somewhere, right? So we have tabular structure where we can represent this 3 address code. Let me show you here representation of 3 address code, right? Representation of three address code. So first representation will be quadruple. You may have heard about quadruple. If not, then here we are saying what happens in quadruple. You will just represent these whatever operators being used, operands and the results. You will prepare the table operator, operand 1, operand 2, and result, right? So suppose this is the first position. What is it? Plus operator. It will be A and B are added and result is stored in T1, right? In second case, what happened? Suppose T1 was stored in minus T1. I am storing minus T1 is being stored in T2. Okay. So here you are maintaining 4 columns, 1, 2, 3 and 4, right? So let me write like you are using 4 columns. Okay. Now you can keep these statements like it is on number 2. You can keep it anywhere, right? You can keep it in fourth number or fifth number, no problem, right? Yeah, order might work. Order is important, but if you are not having any order issue, you can position somewhere, right? Now, but you can understand it is 4 column extra space. can we work with just 3 columns? Okay, so let me tell you another example, another way of representing 3 address code. Okay, suppose I am taking red color. So the another example, if this is number 1, then we are having now number 2, it is triples. Okay, so here we will use just 3 columns. In place of all the 4 columns, we will use the operator, first operand and second operand. We will not use result column. Okay, I, operator 1, operator 2, and that sorry, where this is operator, this is operand. Wait a minute, operand 1, operand 2. Okay, so what will happen? So in this case, what will happen? You will use in first the same thing plus A and B, right? In place of having this another variable here, another column for result, you can assume that the result is being stored here in the first, right? So you can use this number 1 in place of this thing, T1, if at all somewhere you are using T1 like here. So here you can use minus in bracket 1. So the result of this statement will be used here. However, we can't move the statements easily. You cannot place this statement before 1, right? And that is the thing we are talking about here in triple. So it has advantage that we are having we are taking less space. However, we cannot move the statements easily. Here in the quadruple, what is happening? We are having 4 columns. We can easily move the statements somewhere, but it is taking some space. So it is our way. Another way of representing this 3 address code can be indirect triple. So in this indirect triple, we will try to manage the space as well as we will try to have the movement of the statements also. So now here what we will do in this case, we will keep some information of memory location. How? Suppose the first, where it is stored, at any memory location. And suppose second is also stored at 21 location. So in this way, along with the results, we are just having the memory location. So if we have this memory location, we can keep the statements, we can move the statements wherever we want. So the problem of triple is eliminated, as well as the space, although it takes a space for storing the memory, but still it is less than quadruple. So these are certain things that we have seen here in 3 address code as well as intermediate code representation. So basically 4 things that we have seen here in intermediate code representation. It was tree form or linear form. So in tree we have seen syntax tree, DAG tree, and in linear form it can be postfix and 3 address code, and we have elaborated a little on the 3 address code, and we have seen different representations of 3 address code. So that is all for intermediate code representation, and thank you.